we'll go ahead and get started here. Welcome back. I'm Dave Judy, your host today. Welcome back to the webinar series where we've been having a series of talks on grid resilience. In this series, we've been excited to share with you some of our current research efforts here at PNNL that are addressing grid resilience, considering both climate change and also looking at clean energy transitions. In our first session, about a month ago, we heard from some of our PNNL grid research experts where they discussed some of the challenges facing the grid, including some of the tools developed to support grid resilience through modeling. And that's really that cyan box here on the screen. In our last session, we had our first talk discussing local scale extremes, where we heard about some of our wildfire research activities here at PNNL. This included some of the capabilities that have been developed that utilize remote sensing technologies and the development of a machine learning model to understand future wildfire behavior in a changing climate. Our next couple of talks will continue along this theme of understanding local scale extremes. This includes today's topic of resource drought, and our next session in 2 weeks focused on floods and hurricanes. Our final session will go down to that bottom blue box, discussing some of our exciting new research and tools used to represent technological change in our energy system portfolio and what that means for grid resilience. For today's topic, it's my pleasure to introduce to you Natalie Voisin and Xia Feng. Dr. Natalie Voisin is a water resources engineer in the Earth System Science Division here at PNNL. She leads interdisciplinary research on regional water energy dynamics for the Department of Energy. She also holds a dual appointment as an associate professor in civil and environmental engineering at the University of Washington. Natalie's expertise is in coupling climate, hydrology, and water resource management models with power system models, including production cost and aggregated building energy demand models. She uses her expertise to develop climate intelligence for the evolving power grid and support power grid engineering and market development that takes into consideration advances in earth system sciences and services. She holds a PhD in water resources engineering from the University of Washington. Dr. Xia Feng is an atmospheric scientist in our Atmospheric Science and Global Change Division here at PNNL. She also holds a dual appointment as an assistant research professor in the Department of Meteorology and Atmospheric Science at Penn State. Her research interest lies in using atmospheric data and models to advance understanding and modeling of human influence on Earth systems. She's an expert in estimating carbon budget and the surrounding uncertainty from urban to continental scales using atmospheric data and models. Since she joined PNNL in 2020, so not long ago, she's extended her research interest to global and climate scales, specifically studying carbon climate feedback with the land-atmosphere interactive system. Dr. Feng holds a PhD in geophysics from the University of Science and Technology of China. So with that, I'll turn it to Natalie and Xia to present on resource drought.
Thank you so much for the introduction. Let me go to the next slide. Okay, next slide again. Okay. Oops. Sorry, I'm having some issue on going back. Carly, sorry, can you help me because I can't see on my screen how to get back on this one? Perfect, thank you so much. So let's talk about resource drought. And on this slide, it's a little different visualization that you had that Dave showed. And this is just to show how resource drought differ from a mechanism perspective with respect to other local extreme events. When you look at the grid, you do have electricity demand. You and I and all of the utilities and all of the human systems. This demand is going to be met at all times and within security constraints by a number of generators. So you have this management component that is sending the signals and managing the electricity and the economic components so that the demand is met at all times. And then you have the delivery, transmission lines and distribution line that is going to make sure that the generated electricity is just meeting the endpoints, the demand. What we've seen so far, we've seen how wildfires, and we're going to see how hurricanes and floods are impacting the infrastructure. And we're talking on operations and outages. What is specific about resource drought is that we're not looking at forced outage. We are looking specifically at operations. We are missing the fuel. So that is the introductions on how we're going to approach resource drought. It enters grid resilience through generators specifically. See, next slide. Perfect. So those generators, there are over 11,000 generators across the US. And it's important to note that we use multiple technologies. If you look at the map, not only we use multiple technologies, but all of those generators are located close to where the demand is and also close to where the resources are. Next slide. Oh, okay, now I know. So let's talk more about those generators. Over in 2021, this is the generation portfolio that we had over the entire US. The different colors is for the distribution of the use of those generators. What's important to note is that solar is the technology. It's about over 1% of the capacity, and it just relies on irradiance. This is the fuel. For wind, the fuel is also the wind. For hydropower, it's the water. And one of the technology that we underestimate is actually the thermo-electric. You see, it's all the purples on the pie. There is a lot of thermoelectrics in today's grid, and it turns out that for this one, water is not the main fuel. It's going to be natural gas and coal, but it's an important component of that technologies for cooling. So this is part of as part of the resource drought that we're going to talk about today. We're going to talk about those 4 technologies that rely on both water, solar, and wind to function as it's supposed to do. Next slide. Okay. Something that you may not have heard about resource drought in the past. We've talked about drought, but here we're looking at how the generation mix had changed over the last 20 years. Something to notice here is to see the black line. This is for wind, and the wind has become a prominent source of generation across the US, especially since 2005. When it comes to solar, it's really after 2015. So from a climate perspective and a science on resource drought on the electricity sector, everything that has to do with wind, solar, compounded with water, it's relatively new. And why does it matter? When you looked at the magnitude at this time, if you add wind, solar, and hydro together, they actually exceed nuclear, and together they actually reach the same level as thermoelectric plant generation during the low peak. So understanding resource drought at this time is important, not only from a grid resilience perspective, but also from an economic perspective, as we're going to talk about today. Next slide. So the outline and what the way that we've organized it for you is that first we're going to talk about water, and then Shah is going to talk about wind and solar drought, and then we'll bring them together at the end. Next. So let's talk about water. We're going to talk about hydrologic and reservoir drought. We're looking at first what's the impact on generation and why we should care. Have it from a simulation perspective of what simulation is bringing to the research and our understanding of grid resilience. we're going to look at that projections of droughts on the grid under future droughts and under climate change. And then something that we will want to mention is that it's not just a water quantity, but it's water quality. And finally, we're just scratching the surface with those water quality and quantity. Some of the last word and take-home message will be about the other ecologic and social economic droughts. Next slide. Thank you. So again, both hydropower and thermoelectric plants are impacted by hydrologic and reservoir droughts. What you have on those two maps here are the locations of those two technology. The hydro on the left, the size of the pie is for the capacity, and you see a lot of the capacity is in the Western US and on the Eastern US. Something to note is that when you start from the northwest corner and you go down to the southwest corner of the US, what is not where climate intelligence comes in is that this is not the same interannual variability in precipitation. It means that when you're talking about the droughts in the Northeast, typically it's for 1 year and it's pretty moderate. When you're talking about a drought in the Southwest, there are years where it's very wet and there are years where there is nothing, and over multiple years. So the reservoirs that you see in the Western US, typically, especially the Southwest, they operate for multiple years. So this is why now we're talking about managing, one drought. It's typical. We are right now in a mega drought, and we're getting to that end of what the management can do. So this is something to note, that the difference on approaching droughts when it comes to hydropower, there are differences between regions. Same thing for the thermoelectric plants. You see that they are pretty widespread, much more on the Eastern US. And there's plenty of water on the Eastern US, but what defines resource drought in the Eastern US is not just going to be the water quantity, but it's going to be limited by the water quality and the stream temperature in particular. So approaching the water droughts and the impact on grid resilience in the US, it's a regional matter. And the work that we've done so far at PNNL, we've focused on the Western US, we've focused on Texas, and we've focused on the Southeastern US as well. But let me focus on the Western US for now. Next slide, please. So the Western US, and let's look at what a drought is. There's no such thing as a drought or one drought. You're looking here at 20 years of soil moisture over the Western US. Every time it's dark red, it means that this is a very severe drought. It means that all the water management, it's really what's left in the reservoirs to manage and supply the water for the different sectors. Something to see here is that there is not a single drought that is the same. I want you to focus on 2001, 2015, and 2021, which were noticeable drought in the Western US. All different. And next slide, please. Based on observation, we just want to know how drought matters. With those 3 different droughts, you can see here the impact of those 3 droughts on the hydropower generation over the Western US. 2001, which didn't seem to be that bad across the entire Western US, actually was the worst from a hydropower perspective with minus 21%. So the point here is that first, drought matters, it impacts hydropower generation, and all the different droughts needs to be considered. The seasonal dynamic of droughts, here we were looking at 21 years and none of them were the same. If we want to have a good perspective of what a drought and how a drought can threaten the power grid operations, we need to go to modeling. Observations are not enough. In those last 21 years, I've shown before how the generation portfolio has changed. So it's important that we use modeling to understand how a set infrastructure can go through a whole range of different droughts. So this is why we use modeling. Next slide. And here is how the modeling looks like that we are using at PNNL. Depending on the science questions and some of our partners, for very quick research questions and very quick turnaround, some partners like to use observed past hydropower operations. So we have a way to integrate them in power system models to address the science question. For longer term, we are looking at either observed climate or we're using climate projections. We then input those into microscale hydrology model. We developed our own large-scale water management models that allows to have reservoir operations and water allocations for different sectors of activities. And we get those reservoir storage and release. We turn them into hydropower operations. We also use thermo-electric plants. We derate them based on the water quantity, and those inform the power system model. At the seasonal scales, water drives the water. So we have hydropower going into power system models. When we're going to the scale of the grid operations within a week, within a day, then we have the power system models that fits into the hydropower. That's one of the nuances that we use in our model toolchain. So with this modeling toolchain, if you go to the next slide, here's what we demonstrated. We use the historical, the grid, the power grid from 2010, and we use 55 years of historical climate to demonstrate the impact on the hydropower and the power grid. And what you have here is those 55 years. The dark line is the hydropower generation. You see how it goes up and down. The gray line is the thermoelectric plant generation. And so within the 2010 grid, what's happened during a drought is that when there is a resource drought on a hydropower, this is being compensated by other technologies and here by the thermoelectric plants. It has a lot of impact on the power grid. First, the system cost, because the thermoelectric plants are more expensive. And we're talking of variation of -8 to +10% variation in system cost. What it is, it's the price of electricity. That's your wallet. It also has an impact on greenhouse gas emissions, where we have also large variation, and it's important to understand if we are meeting our greenhouse gas emission goals or not. The other things to notice is that it's one thing to transfer from one technology to another. Here we're going from hydropower to thermoelectric plants. If you go to the next slide, thank you. You remember that those are not located, they are not co-located. On this map here, remember over the Western US, a lot of the hydropower is in the Northwest, but most of the thermoelectric plants are in the desert Southwest. So it means here that we have a dipole during droughts and wet periods where the generation it will be more in the Northwest or in the desert Southwest. It turns out that at that scale, it's a pretty large grid. This is what we call a mesoscale. And it means that during certain climate phases, when it's wet in one part, it's going to be dry on the other one. It's very convenient for the grid operations here. This one is the El Nino Southern Oscillations. And that is why we've been showing here on the patterns on the right, that whether you're in an El Nino or a La Nina, it turns out that the cost of operation is about the same because you always have one region to compensate the other one. However, during a neutral phase of that oscillation, what we call neutral ENSO, this is when you may have droughts that are not as severe locally, but they are widespread over the entire Western US. And we've demonstrated that this is during those events that actually the resilience, the reliability of the grid, we were getting closer to having unserved energy. So with this climate intelligence, we are basically designing drought events that are the most at risk for the power grid with the infrastructure of today. And so we need to think about what those future droughts at risk are going to be with the future grid. If you want to go to the next slide. Thank you. So we've been talking about those drought dynamics and how we play with how the grid is structured. We've demonstrated that whether this is climate change or whether you have drought, and drought is not climate change, but there are impact on the water availability in general. There are going to be regional impact. So California and the Northwest are directly impacted by changes in water availability. but this is going to impact the regional import-export. And there is a switch where if it doesn't come from the Northwest to meet the Southern California demand, which is a driver for a lot of the grid dynamics in the Western US, then it would come from the desert Southwest. So we see that through the import-export dynamic of the grid, water availability, water droughts as a way to propagate through the grid. There are other mechanisms that we've been pulling forward. It's not just import-export, we're also looking at economics ways of propagating drought resources. And we have been looking at market spillover when there is a disruptions in California markets due to drought and especially high temperature. It actually propagates to the Northwest market. So we really need to understand better those resource droughts and predict them. Next slide. Beside this, understanding those different drought dynamics, we're also looking at the impact of climate change on federal hydropower. Just last week, the third assessment of the impact of climate change on federal hydropower got published. And this is here an example of how we contributed to this report. And we used the tool chain to understand the impact of climate change on federal hydropower. Something specific about climate change is typically the uncertainties. So we've been working here on understanding where this uncertainty comes from and how to communicate it for decision making. So the different colors that you have here, it's the contribution of the different processes in the tool chain to the overall projection. When you have a lot of green, it means that the uncertainty in the projection, the range of projection in hydropower, most of it can be explained by the range, the uncertainty in the climate model. Everything that is yellow, it's actually the uncertainty in the way that we represent the hydropower operations themselves. So you can see that those are very regional and type of research that we do to communicate and work with the hydropower operators on making long-term planning and resource adequacy studies. Next slide. We've talked a lot about hydropower. On each of them, we were also derating the thermoelectric plants, but maybe it was a bit of the background of this presentation. So we want to show here what we're doing with thermoelectric plants. We are quantifying the thermoelectric capacity at risk. We've worked over Texas, and we've worked on assumptions on reservoir level threshold for which water releases cannot support cooling. So the thermoelectric plants are typically downstream of the reservoirs. And if you reach that threshold, then you know that the downstream capacity might be completely out. And so we've been designing those droughts, and then we've been looking at the probabilities that certain capacity would be at risk. We also work on the southeastern US, where here, as I mentioned in the introduction, it's not about the water quantity, it's about the water quality. So we've been looking at the cooling potential. So we have 4 rivers, and we are looking especially at the diagram most to the right. That's the cooling potential, the cooling that is required for the power plants to function at maximum capacity. And you see that it starts going down. So we are looking here, depending on where you are in the river. So it starts from the headwater to downwater. Every time you have a line, this is where one of those reservoirs are. As they store water, they change the cooling potential because of thermal stratification. And then that really helps better understand the evolutions of that cooling potential for operations. Next slide. So we've been talking about water quantity, water quality, but we're just scratching the surface. In fact, there are multiple droughts, and they all impact grid operations, whether those are meteorological droughts, where we just have dry weather patterns, and here it's going to impact thermoelectric plants or just no water. Hydrologic drought is when you have no water in the river. This is the one that we've talked about the most right now. There's also agricultural droughts. this impacts the grid, because if you don't have enough, when the crop starts being affected by the drought, then it's also changing the electricity load. You stop pumping, or you don't pump at all anymore. And this is changing the electricity load and the water availability, which propagates to the grid at some point. Social economic droughts, that impacts other sectors with water as a commodity. That impacts navigation, for example, when some resources cannot be met, or when we are curtailing aluminum smelters on the grid during droughts. Those are socio-economic droughts. And ecological drought it goes back to environmental regulations, when it's all about conservation. So at PNNL, we're also looking at those different droughts. Next slide. Ecological droughts to start with. Ecological drought is a science in itself. And you have new environmental regulations because we might not have realized what was the stress on conservations. So this is something that keeps evolving. And over the Northwest, over the BPA system, there's been a recent change in environmental regulations that we call the flex bill. And we run over these regions with and without the flex bill, understanding what was the change in hydropower generation and compared to what the power system was expecting. And this is this other graph that you have at the bottom right here, where with prior to the environmental regulation, this is how much the power system was expecting for its resilience studies, but this is not feasible anymore because of environmental regulation. And that's normal. This is something that is going to happen in other regions. But that's what the point here is to say that this is something that is evolving, and we need to consider ecological droughts in grid resilience, because we had 9% of the annual hydropower that was non-feasible anymore. And 2/3 of it was associated with this regulation. 1/3 was associated with how hydropower is represented in the power systems, and that's also something that we are addressing at this time. Next slide. And this is one other example of the other drought. This is here a social economic drought. We've been looking at how droughts are affecting farmers and their way to adapt to droughts. They are going to change the crop that they use has a different economic value. Their objective is to maintain the economic revenue, and it's also going to affect how much irrigated area, how much area they irrigate. All of this is going to have impact on the load and for grid resilience, but also from an economic perspective, those sectoral dynamic comes back to the grid through the load and water availability, and then again through the generation. So we need to understand more about how to integrate social economic droughts in grid resilience. And with this, I will move to wind and solar for Shah.
Thank you, Natalie, for the introduction of the diversity of the different resource droughts. So what I'm going to present here is to showcase some wind and solar droughts events at the different time scales and what we have done at PNNL's on potential ways to tackle them. The two maps at the bottom are the deployment of solar and wind energy in the US. The first case is the solar droughts that happens in the California Independent System Operator regions. The second case is a focus on the BPA Balancing Authority region, which is kind of on the northwest of the US, in which most are like wind with a little bit of solar. So the third case is a resource drought like lasting for more than 3 months that severely affects the Texas ERCOT market. Next slide, please. Okay, so the first two cases are the shorter time drought events up to the few days. So the image on the left is a modest satellite image reflecting the smoke from the wildfire events during the middle of September 2020. a large area is covered by heavy smoke. The heavy aerosol loadings from the smoke blocking all the sunlight and reduce the real-time dispatch by 20% at the left bottom panels by during these events compared to the climatologies. And the figure on the right is the time series of the load and the generation from the BPA balancing authority during the recent heat wave events. So the green line here indicates all the variable energy generation in the BPA, but as I mentioned earlier, it most wind, a little bit sun, solar. So there is the multiple day period with a very low renewable energy generation. If you look at a figure from August 5th to 9th, almost no renewable energies was generated. Next slide, please. So we did some stats on the variable energy generation in BPA for the past 18 months to study how often this resource drought events with a low energy generation happens more than a day. Here we use 500 megawatts as an arbitrary threshold for the low energy generations. So we find at the lower bottom on the left, so we find more than 25% of the time, BPA has experienced a low generation of the energy for more than a day, and in which 5% of the time actually lasts more than 60 hours. Next one, please. So the third case I'm going to show is the famous month-long resource events droughts happening in 2015. This event happened in the first quarter and extended to the second quarter. So the image in the is the screenshot I took from the website showing that large area experienced 20% of energy reductions. And this area, if you look at figures on the right, actually hosts a large number of the wind turbines owing to the abundant wind resource climatologically. So for these events, wind industry did not anticipate such a low wind episode. Some companies even experience financial problems due to the lack of the energy productions and the revenues. Next one, please. As an admin scientist, my interest is how to improve the numerical weather predictions to support the operation, management, and planning of the energy systems. So if you look at the figures, I want to point out the forecasting scale varies with the spatial and the temporal scales. So the figure on the left showing that the current forecast scale as a function of the lead times. With the improvement of the technology, our current forecast systems are quite skillful a day or a few days ahead. The example are the score lines and the hurricanes on the right. So in general, error in the numerical weather predictions grow over time because of the nature of the chaos or so-called butterfly effects. So predicting the weather on the particular days beyond 2 weeks is extremely challenging, particularly for the sub-seasonal to seasonal timescales. This horizon, however, is very important for the operation management and planning of the energy systems. The atmosphere phenomenon at these longer timescales usually are large-scale, low-frequency phenomenons, such as Rossby waves on the top figures of the right-hand side, long-range teleconnections, and El Nino. So we usually call this recurrent and persistent large-scale atmospheric circulation patterns as a weather regime. Next slide, please. So our question is, how do the weather regimes drive the wind speed and the power productions in the US? Next, please. So supported by the DOE's Wind Energy Technology Office, we at PNNL have studied the impact of climate scale phenomena on the wind resource in the US. So I'd like to point out that there are not very many studies on the topic in the US. So, okay, here's the results that we use a machine learning approach and identify 4 types of weather regimes affecting North America. Alaskan Ridge, Pacific Trough, Arctic High, and Arctic Low. So these weather regimes are more distinct and stronger in the cold season than in the warm seasons. This weather regime has very strong teleconnections with the climate mode. So on the top, Alaskan Ridge and the Pacific Trough resemble the Rossby waves trains associated with the positive and negative phase of Pacific North America patterns. And on the bottom, Arctic high and Arctic low indicate strong meridional pressure gradients associated with a combination of two phases of North Atlantic oscillations and El Nino. Next, please. So we take the cold season as the example. The two PAN regimes have opposite effects on the wind speed and the wind and the power productions. Alaska Ridge is associated with wind and power productions by reductions by up to 20% over the western and the mid-US, while the Pacific Trough tends to increase wind and the power by up to 20%. And on the right, the two NAO regimes also show the opposite effect on the wind speed and the power productions, mainly in the Rocky Mountain areas. Next, please. So the time scale of teleconnections is usually from a month to a seasons, which is happen to be the subseasonal to seasonal time scale indicates the potential of using weather regime to improve the S2S scale forecast. So next slide, please. Therefore, we raise the second question. So to what degree the weather regime can explain variabilities in the wind and the power productions? Next, please. What we focus here is just on the power productions in this presentation. So we study the power productions related to the weather regime as the unit of the markets, those ISO and the research area W52 regions covering the states of Washington and Oregon. So W52 is another PNNL-led wind energy projects sponsored by the DOE Wind Energy Technologies Office, which focused on the wind resource in the complex terrains. Next slides, please. So yeah, this is the result. So this figure shows the explanatory powers of the weather regime to the power productions vary with the space and the time. And for example, on the left corner, the weather regimes can explain the variability of the power productions more than 50% in January over W52 regions, and up to 20% over CAISO, which is California. It has more skills in cold months than warm months in general. Next slide. Okay. So we repeat the same analysis, calculates the explanatory power of the weather regime to the variability of the regional power productions at a different time scale from a day to 3 months. Here, I only show the result for CAISO, W52, and the CONUS as a whole. This is very complicated figures. So, but the main points I want to show is the characteristics of the relationship between the weather regime and the power productions vary with the time and the space. What is happening in the regions could be very different than what is happening overall. Next, please. Yeah, concluding remarks. Natalie will give some highlights about today's resource droughts presentation from the great resilience perspectives. Natalie, please take the floor. Hmm?
Natalie, did you have something to finish off, or we done?
Yes, can you hear me?
Go ahead. Yep.
Okay, sorry, my computer is a bit problematic. I can't put my video on. So we've talked about hydro and how this is impacting hydropower and thermo-electric plants. We've talked also in isolations about solar and wind, and you need to put all of them together to look at grid resilience. When you put them all together here by regions, you see that moving forward, we need to look at individual and compounded resource droughts together. Something that we haven't addressed are the regions that are in the back. Those different colors, they actually represent market regions. Wind and solar are presently must-take. Hydro is following the load or the prices. It really impacts on how all of those resources drought are going to impact the grid at the end. So going into the resource drought research, we need to look at impact-driven analysis. And what we're suggesting here is that market and reserve regions are more important than climate regions. We've also talked about the linkages with other sectoral systems and human systems, and especially with water on impact on agriculture and ecological droughts. So this all linked to social equity, environmental justice, and other human system components that we didn't talk about today, but are at the core of some of our ongoing research. Finally, you see that this is a lot of different technology, and we need data. A lot of data from an atmospheric perspective and climate perspective. We tend to use them at a specific scale. When it comes to doing that grid resilience, we need to combine both the climate and the power grid scales and dynamics. So we have at this time a lot of data needs. And moving forward, regional test beds are really key, but each regional test bed cannot really inform on a different regional test bed. Those are really unique regions to move forward with decarbonization and grid resilience to resource droughts. And with this, I would like to thank you all for your attention, and thank you so much.
Thank you very much, Natalie and Shaw, for this presentation today on resource drought. Very informative. Thank you to those who have submitted questions in the chat. We'll try our best to get through as many as possible before we end here at 12 p.m. Pacific time. Some of the questions were answered but in the chat already, but we're going to go ahead and maybe ask them here so everyone gets to hear it. And so this is a question specifically for you, Natalie, on if you could please elaborate on water quality.
Yeah, thank you. Thanks for this question. I went a bit fast. So in terms of water quality, the one that we are looking the most at this time from a resource drought perspective is the stream temperature. And so we are simulating stream temperature and how you can look at the rivers as a storage of heat. And the way that we've been looking at the cooling potential, it takes in consideration the environmental regulation for the maximum temperature at which you can release the water that you withdraw, and then it gets warmed up for cooling, and then you release it in the stream. There is a maximum temperature and the maximum differences in temperature. So this is how we're looking and computing this cooling potential. And we've been doing it over all of the southeastern US on all of the rivers. And we have the reservoirs that we have a thermostratification model that allows to understand how reservoirs can in some times improve and have cool some of the water, but in some places it rather warms it. So understanding this thermal stratification has been an important process to understand how this was impacting the downstream, but only about 8 miles. After this is really more the air temperature that is the largest drivers of the cooling potential.
Great, thanks, Natalie. Another question for you here. A lot of the ecological impact is focused on hydroelectric plants. How much are traditional steam thermal plants affected by droughts or water levels?
So we are over the Western US. For the most severe droughts with the current infrastructure, we were up to 10% derating in capacity. So that's just a reduced efficiency. For Texas, we were looking, especially for thermoelectric plants, we were not looking at derating, we were looking at the entire capacity at risk with a full outage. And we were looking at 20% of the capacity that could be completely out due to water quantity and low reservoir levels.
Thanks, Noah. Shall I have a question for you here? This is getting into the weeds of some of your numerical modeling. So the question is, what is the current CFL number for the weather prediction model you're using? And then the second part of that is, what is the order of accuracy for the numerical model that you're using?
Thanks. I can briefly answer this question. So during this presentation, what we are emphasizing is the model forecast scale is varying with a spatial scale and a temporal scales. So we definitely has a different accuracies for these different temporal scales. But for these, as Dave mentioned, getting to the weights for the CFL numbers, we usually use 3 in the numerical modeling. Thanks.
So a question perhaps that both of you can take a stab at answering here, and you can decide who goes first. What do you think is needed to improve predictability of resource droughts? And so you might take a water angle and a wind solar angle on this.
Go ahead, Cha.
Thanks. Okay, I can go with that. So, from the atmospheric scientist perspective, in my opinion, we need to improve the model forecast scale at the different time scales, right? Particularly at a longer time scale where the model forecasts are very still kind of underperform as opposed to the market needs. In my opinions, like more independent prediction models should be evaluated to better understand their limitation and the potential of predicting those resource droughts events. Another important aspect I like to emphasize is the monitoring. So more accurate observation data are needed, including like ground-based observation network and the satellites. So the observation are extremely useful for the monitoring the droughts and also for the modeling evaluations, and also can improve the model prediction skills by assimilating more observations to the model. And another thing is so nowadays we have more and more like AI and machine learning type of approach to improve the model performance. And the one thing is important to get to build this good AI or machine learning models is having a large, rich data pool to train those models. Yeah. Anything else? Maybe Natalie, you go ahead.
Yeah, from a water perspective, the seasonal dynamic is what we're looking at. So we are looking at different techniques. I would say that I've mentioned that over the Northeast, it's really one season after another. So we're looking at improving the ability to forecast precipitation a season ahead. We have very flashy basins. When it comes to the desert Southwest, issue is interannual variability, multiple year drought. And from a modeling perspective, we are blind. We're still working on understanding and predicting multiple year droughts, and we're a bit stuck. This is why when we're looking at water availability, predictability, we're also looking at plan B with how much we can store. It becomes a storing issue. Some of the things that I would like to mention as well is in terms of time scale, we're looking at a much shorter time scale. Right now, you have the part where water drives the hydropower and the thermoelectric plants. And then there is that scale where it's the grid that starts driving the hydropower operations and the and the cooling. And that it's something where we have a switch from what is the most important driver And in the modeling perspective and the coupling perspective, we need to understand how much we can translate, how much we can move water from one week to another with the understanding on the impact on the water side. So it's not really drought, but it's water availability, and it has a tremendous impact on how we can mitigate and alleviate the resource drought in wind and solar.
John, another question for you. For the modeling, how do you quantify and evaluate sky cloudiness?
So we need two variables. So in the model, we directly output the cloud and cloud-related variables such as cloud fractions, cloud water, liquid water, and ice water, something like that. And then with all the, to evaluate those model variables, we use a different approach. For satellites, we have those variables, and also for ground-based instruments, we can get the cloud fraction mainly, and that's how we evaluate and quantify the sky cloudiness. Thanks.
Right. Maybe another question for you here. What are the advantages of studying weather regimes and their connection to renewable energy?
So the weather regimes are those recurrent and persistent large-scale circulation patterns. So the current models has some skills to predict weather regime, but almost impossible to predict weather events on a particular day 2 weeks ahead. So once the relationship between the weather regime and the renewable energy resource is characterized, study the change in the weather regime along with the changes in the future scenarios can help us understand the impact of climate change on the change in the wind resource in the future. So for example, in this weather regime study I just presented, the places have a stronger dependence of the local wind to the weather regime, indicates where the power production is sensitive to the change in the future climate. Thanks.
Thank you, Shaw. So this next question is maybe a little tough, but excited to hear your responses. If the decarbonized grid is becoming more vulnerable to resource droughts, how is a decarbonized grid more resilient? Natalie, maybe you want to go first.
Yes. So it is becoming, first from an economic perspective, this is a fuel cost. So I want to mention from an economic perspective the advantages that also comes with making the energy in the future, the energy and renewable energy accessible. Where it gets the resource drought, like we've seen with climate intelligence, we've seen that you never have one drought over all of the resources and the technologies at once. So some of the things that we are actually starting working on is understanding how climate intelligence can come and inform transmission, can inform storage design with scales that are not necessarily assigned to how thermoelectric plants were working until now, but if you're looking at the different markets of today, they're all along how much you can store it with thermoelectric plants. But if we're changing the generation portfolio, we really need to rethink on what the market should be. The storage is different. You have different technologies. Our understanding and our ability to predict it is also different. So should the market be day ahead and real time, or should it be a week in and now? When you're looking at balancing authorities and you're looking at how much to balance the demand and the generation, this was based on markets. Well, now if we look at where the resources are, can you rethink it, making sure that it's more resilient? So there are really a number of infrastructure at the power grid that I think needs to be challenged, and we're really developing the climate intelligence for that. You're muted, Dave.
This next question perhaps is a little bit of a follow-on to that. And speaking of some of the recent or events we're experiencing currently. So we're seeing what a mega drought can do to energy resources in the West, and specifically California and the Colorado River Basin. And we saw what a cold snap can do in Texas. So what do we learn from those events for a resilient and decarbonized grid?
Do you want to take this one?
Sorry. Natalie, why don't you go ahead?
Okay. So first, the cold snap. I think it really brought into perspective the market part, and it was an unprecedented event from a climate perspective. So from a climate perspective, we already work a lot on statistics, understanding what are the extremes and the tails of the extremes. So I think that when we come in testing grid resiliency, at this time in resource adequacy, up to 5 years ago, grid resiliency was testing one representative year, one weather year. And I think that whether those are the mega drought at this time or the cold snap, I think it really shake up a bit the system, saying that we really need to understand what are those climate events that are at risk. And this is not just on the infrastructure, like was perhaps the cold snap, on how there is an outage, but we're also putting emphasis on the energy droughts, and how even the energy drought can really substantially disrupt operations. So with the mega drought at this time, we're still trying to figure out, I think it's providing a lot of incentives to put more research in multiple year droughts, which at this time, in none of the resource adequacy that we have over the Western US, we now look into droughts, but 1 year droughts. We haven't looked at multiple year droughts. So hopefully this is something that we can do very fast.
Yeah. So what I want to add is, so for this one drought, and then what we learn as the presentation last slides was showing there's all the energy, renewable energy is kind of regional, has its regional features, but how can we utilize or just take advantage of the different renewable energies, and then to help us to reduce the impact by those, like Texas cold snap events would be a good strategy, I think.
Thank you very much, Natalie and Shaw, and for everyone that submitted questions today. It's been a pleasure being with you. Just a reminder, we have 2 more of these talks scheduled. In 2 weeks, we'll hear Resilience to Hurricanes and Floods, presented by myself and Karthik Balaguru. And then in about a month, we'll be having another talk, our final talk on resilience to energy supply and demand changes, presented by Gokul Iyer and Jenny Rice. With that, we'll end today's session and see you in 2 weeks.